Okay, so last week we talked about discrete probability distributions with our binomial and geometric and the Poisson distribution. This week we're going to talk about continuous probability distributions, mainly the normal distribution. Now there are different versions of the normal distribution. They're all continuous. Remember, continuous means that there's an infinite number of values in between any two points, any two numbers. So that means that the probability of a single number of occurring has to be 0, because if there's an infinite number of them, they would add up to be something larger than 1. And so when we're dealing with continuous probability distributions, we're looking at the probability of being within a certain range rather than being equal to a specific value. It is a bell-shaped unimodal density curve. Remember, it is that, oops, get back here. It is that bell curve like that, unimodal, one peak. The area under that whole curve equals 1. So that whole area under this thing is equal to exactly 1, because that is our probability distribution. And all the values, all the probabilities of a distribution have to add up to 1 to be valid. And the probability of observing a value in a particular range or interval is calculated by finding the area under the curve. Let's say this is value A and this is value B. If I wanted to find the probability of our value being less than A, that would be this area over here, less than A. If I wanted to find the probability of a value being greater than A, well, that would be this area over here on that side of A. If I wanted to find the probability of a value being between A and B, well, that's the probability in between them here. So the question is, how do we find those probabilities? I'm going to get this out of the way so we get the rest of our slide up. How is that done mathematically? Well, it is done using calculus and an integral in calculus. Integrals in calculus are used to find area under the curve. To avoid having to use calculus, we use a couple things. Either we use technology, the calculator, Excel, or Minitab, or we use a standard normal distribution table that is in your textbook. So as the standard deviation increases or decreases, the curve changes shape. So there's a curve with a medium-sized standard deviation. If it gets to be a larger standard deviation, you know that curve gets flatter and wider. If the standard deviation decreases, it gets narrower and taller. So there's that average size standard deviation. If we get a smaller one, it gets taller like that. So again, the wider curve here is a larger standard deviation. Narrower curve has a smaller standard deviation. They do have the same mean. The center is exactly the same. Now, if I'm asking which one has a standard deviation of 3, well, that wider curve, you go out 3 and then 3. Notice it's not all the way out. That curve keeps going off our graph. You go out another 3. Most curves would go about 3 standard deviations in either direction from the mean. Which one is a standard deviation of 1? Well, that inner curve, see, 1, 2, 3, gets us out there. Some things about this normal curve. You'll notice that if we go out 1 standard deviation below to 1 standard deviation above, the curve is bending downward. It's called concave down. But outside of that 1 standard deviation on either side, it now turns and it's bending upward. It's concave upward. Now we start out talking about probably the most versatile and most used distribution, normal distribution. This is the one that's in the table that we would use in your textbook. It's called the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. It is actually the distribution of the z-scores. So we use z for a value on this curve. And it's also called the z-curve. So any number, z prime, is just the number that we're trying to find the probability for. it goes anywhere from, now they're just saying from negative 3.89 to positive 3.89, can be found in the table in your book. And the only reason they limit it to negative 3.89 to positive 3.89 is that's as far as the table in your book goes, is out to those z-scores. To use the table, we have to find the correct row and column to create the z-score that we're looking for. Rather than just making a list of all the possible z-scores, they put the first two digits in the front column and then the third digit in the top, and we look at the intersection. For example, negative 1.62. Now, the table always gives us the probability of being less than a specific value. Here, we're looking for the probability of being less than negative 1.62. So that's going to fit our table perfectly. The row we're going to look for is the first two digits, the negative 1.6. That's the ones and the tenths digit. And the column is going to be our hundredths digit. That's the 2. So here we've got negative 1.6, and here's the 2. Those combine to make negative 1.62. We trace to see where they intersect. That's a probability of 0.0526. Suppose we wanted to find the probability of this being less than 2.31. So we're going to look up 2.3 and then the 0.01. 2.301 gives us a 0.9896 probability of being less than that. Now, both of those probabilities, we were looking for the probability of being less than a certain value. If we want to get the probability of being more than a certain value, we have to use some of our rules of probability. The table is going to give us this probability here, so what we're actually looking for is the complement of what's in the table. So we look up the 2.31, so 2.3 and then 01. We get the 0.9896, but since it's to the table gives us the probability to the left, or less than, and we want the greater than, or probability to the right, we use the complement. 1 minus that probability from the table gives us 0.0104 is the probability of being greater than 2.31. We can also use the table backwards. We want the probability of finding the value that goes with having a probability of being 2% being smaller. So it's basically the second percentile is what we're trying to find here. So we're working backwards. We want to find the number that corresponds to a probability of 0.02 being less. So we look at our table. We're using in the body of the table now here, looking for 0.02. Now we're not going to find it exactly, so we find values that are close to it. The closest one, the 0.0202 is slightly larger. The 0.0197 is slightly smaller. It's going to be closer to the 0.0202. So that's the one we use. It corresponds to a negative 2.0 and then 5. So negative 2.05 is that z-score. Suppose we are interested in finding the z-value that corresponds to the largest 5%. Well, if it's 5% up here, that means it's 95% down here. So we're looking for that 95th percentile. So we make that switch. Since it's 5% greater or 5% to the right, we need the probability of being to the left or less than, which is that 95%. Now, once again, that's not in our table. We find the 0.9495, which is less, 0.9505, which is greater. Unfortunately, neither one of those is closest to the 0.9500. It's exactly in between them. So because it's exactly in between them, we choose a number exactly in between these two. So it's 1.6, but we can't choose between the 04 or the 05, so I do 045. If I add those together, 0.04 plus 0.05 and divide by 2, I get 0.045. So we use 1.645. Not 1.64 or 1.65, it's right between them. So finding those probabilities under the normal curve can be done without, even if it's not a standard normal distribution. What we have to do is we have to turn it into a standard normal distribution. We do that by calculating a z-score. So our values are now represented by x. They're not z-scores anymore. We're going to convert them to z-scores. So here we're going to find the probabilities under the normal curve. If x is a random variable whose behavior is described knowing its mean and its standard deviation, then we can approximate, or we can actually find the probability of x being less than a certain value by using the z-score of that value and then using that standard normal distribution. Same for greater than or in between. We just use z-scores. So z is the variable whose distribution is standard normal, and x is the value that has a distribution of the mean of mu and standard deviation of sigma. We find the z-score of each x value using the value minus its mean divided by the standard deviation. That gives us its z-score, and that's what we put in the standard normal distribution. So let's do an example of this. So data on the length of time to complete registration for classes using an online registration system gives the distribution of the variable, where x is equal to the time it takes to register, giving us a mean of about 12 minutes and a standard deviation of 2 minutes. So there's our distribution. X is the time to register, and the mean of x is 12, and the standard deviation of x is 2. What is the probability it'll take a randomly selected student, less than 9 minutes? So this is the probability that x is less than 9. So the mean is the center of this curve. That's 12 minutes. 9's over here. We want the probability being less. Well, in order to use the table, we have to find the z-score of 9. We have to standardize it. So 9 minus the mean of 12 is -3 divided by 2 is -1.5. That's the z-score. So what we're finding is we're going to find the probability that z is less than -1.5. We look that up in our table. -1.5 corresponds to 0.0668 in the table. That's the probability of a z-score being less than -1.5 on the standard normal distribution. That's the probability of the time required to register for classes being less than 9 in this distribution. What if we want the probability the student will take more than 13 minutes? So again, our mean of 12 is here. More than 13 is over here. So once again, we standardize the 13. 13 minus 12 is 1, divided by 2 is 0.5. So what we're finding is the probability that z is greater than 0.5. Now the table finds the less than probability. So we find the probability of being less than 0.5, and we subtract it from 1, giving us 1 minus 0.6915, or 0.3085. That's the probability of being greater than 13, or having a z-score greater than 0.5. Now let's say what's the probability of having a student's time being between 7 and 15 minutes. So we're looking in the middle of the curve here. To find that, we calculate the z-score for both of those. 15 has a z-score of 1.5. 7 has a z-score of -2.5. So what we are finding is the probability of z being between -2.5 and a positive 1.5. So we look up those two values in the table. Probability of being less than 1.5 is 0.9332. Probability of being less than a -2.5 is 0.0062. We subtract those to get the probability of being between them of 0.927. Let's go the other direction here. We want to set up our system to cut students off at a certain amount of time. So let's say they're registering and they get distracted or whatever and accidentally leave their registration open, just so that there isn't scandals or frauds in registration. They want the system to automatically log you off at a certain point in time. We want to set that so that only 1% of students will get cut off if they're trying to register. So we're basically looking for the 99th percentile. So that 1% or 0.01 up here corresponds to 0.99 or 99% there. That's the percent given in our table. So we look in the body of the table for 0.9900. The value that is closest to that is 2.33. So that's our z-score. Now we have to solve that backwards to find the actual data value. So I'm going to do that up here quick. 2.33 equals x minus 12 over 2. To solve that, we multiply by 2 to get rid of that. So times 2 gives us 4.66 equals x minus 12. And then we add the 12 to get x by itself. So that gives us 16.66 is that value. So if we have the system cut you off at 16.66 minutes, only 1% of the students will get cut off if they're legitimately still registering. So I'm going to go through these now using the calculator so you can see how the TI-83 deals with these. So I'm going to come back here to the standard table here quick. I got to change my window just a touch. There we go. Oops, that's not what I wanted. There. I have to expand it a touch here too. Okay, so I got my calculator moved into the viewing window here as well. So let's go back and look at these probabilities. So here we have students with again, it takes a mean of 12 minutes to register with a standard deviation of 2. Well, what is the probability that a student takes less than 9 minutes? So if we don't want to go through the problem of finding z-scores, we can use the calculator here using our distributions menu. Second, distributions here. We never use normal PDF. We're always looking for CDF. Now the CDF gives us the probability of being between certain numbers. So to be less than 9, we're going from a negative infinity. We just do negative followed by 6 nines is one way of entering negative infinity on the calculator. There's a couple other ways, but that's the simplest one. Is you have to use the negative. That's this negative key here followed by 6 nines. That's negative infinity. Our upper limit, well, we're going to 9. Our mean of the distribution is 12. And the standard deviation is 2. Then we click paste, and it gives us our function. We hit enter. We get 0.0668. Notice that's the probability we had from our table. A little bit easier to use the calculator because we don't have to go through that process of finding the z-score to standardize it. Let's look through this one. The probability of being greater than 13. So I'll bring my calculator back on screen here. Second, distributions. Again, it's normal CDF. Now we want to go 13 is the smallest up to being greater than. We're going up to positive infinity. So we just enter 6 nines. That's one thing that the calculator recognizes as positive infinity. Our mean is still 12 and our standard deviation is still 2. That's 0.3085. Notice that's the probability we had from the table. Probability being between 7 and 15. I'll go back to the calculator. Second, distribution. Now rather than arrowing down, I can just select 2 here to select normal CDF. Now I want to be between 7 and 15. Mean is still 2, standard deviation, or mean is still 12, standard deviation is still 2. Enter, we get 0.9269, 0.9270 it rounds to, which is what we had from the table. Now this is where it's a little easier. Working backwards, using the table is a little clunky because you couldn't find the exact value in the table, so you had to go to the closest one. And also you had that z-score and you had to solve for that z-score to get back to the actual data value. With the calculator, you don't have to worry about that. The calculator is going to find it for us. So we want to know the probability of being let. Now we do have to remember that the calculator is only, just like the table, is going to deal with the probability of being less. So do second distribution. Inverse normal is option 3. Our area to the left is 0.99. So even though it's the top 1%, we're still using 99 because it's below. Our mean is 12, and our standard deviation is 2. Now this might be slightly different, but this is going to be more precise because the table is rounded off. We get 16.65. Well, the table gave us 16.66. That's because of the round off. Okay, so now we can go back to the presentation mode here. So the next thing we want to look at is, well, how do we assess to see if a population is, or a sample is approximately normal? One of the ways to do that is a normal probability plot, sometimes referred to as a norm quantile plot. So to construct this normal quantile plot, we're looking at the size of our set of data that we're looking at, and we use that to divide the normal curve up into equal pieces of equal probability. So what should happen if the data is normal? We should get a scatter plot that is a perfectly straight line, or at least really close to it if it's approximately normal. So if we have a data set with 5 items, n equals 5, we divide the area under the normal curve into 5 equal pieces. Notice here, 1, 2, 3, 4, 5. They don't look like they're equal, but they are. The area is equal. The length on the axis down here is not, but the area is equal. Each region in this case has an area of 0.2. Again, they're not the same width because the curve isn't the same height. We're looking at equal areas, not equal ranges. Now we find the median z-score for each range. So we find the value in the middle of each. So if each of these has a probability of 0.2, this here would be 0.2, this would be 0.4, this would be 0.6, this would be 0.8. So our median z-scores will be the inverse probability for 0.1. Here would be the middle of that. The middle of this will be 0.3. The middle of this one, I'll put it up here, is at 0.5. Middle of this one is going to be at 0.7, and the middle of this one will be at 0.9. So we do the inverse normal to find the z-scores that go with each of those. And there are the z-scores that go with each of those values. Let me pull up the calculator here quick so you can see how those are calculated. Now again, the median's not in the middle of the region because it's in the middle of the area, half the area on each side. So these z-scores are what's going to be our y-axis of our plot. So the calculator will help us graph it if we want to, or we can use Excel or Minitab. Again, I'm going to jump to the calculator here in just a second to show you where these calculations come from. So we said that this first one was at 0.01. So we're going to do second distribution. We're using the inverse normal now again. Area of not 0.01, 0.1, because it's halfway from 0 to 0.2. It's using a z-score, so it's a mean of 0 and a standard deviation of 1. We get the negative 1.28, which is what we had down here, negative 1.28. If we wanted to find it for the next one, oops, wrong button. Second distribution. Now again, we don't have to arrow down to inverse normal. We just hit 3 and it'll select the inverse normal. Probability there of 0.3. Calculate that out. We get the negative 0.524. That's what we had here. Now, of course, the other side is going to be symmetrical, so we don't have to calculate any more of those. So I just got to arrow through all this stuff quick again to get to the next slide. So once we have found those z-scores that correspond to those, again, we're just equally spacing the z-scores across the plot from 0 probability to 1 probability. We're going to now match them up in order with the data points to create a graph of scatter plot. Now, if they're approximately linear, that means the data is normally distributed. If there's a deviation from linear, they call it a systematic departure, then it means it's probably not a normal distribution. Like here, this is definitely a curve going through here. So that it would not be normal. Here we have an outlier. That outlier would indicate that this might not be normal. Even though the rest of the points are approximately linear or close to linear, that outlier changes it. If we took that outlier out, though, in this case, the rest of the points would be approximately normally distributed. So now we're going to do an example. We're going to construct a normal quantile plot for a data set with 10 values. So the first thing we're going to do is we're going to find the z-scores that correspond to that. So if it's 10 values, we're going to divide this into 10 pieces. So this is 0 here. This will be 0.1, 0.2, 0.3, 0.4, 0.5. When we divide up the other half the same way, this will be 1.0, so this will be 0.6, 0.7, 0.8, 0.9. So then in between there, this is what we need to find the z-score for. This will be 0.05, 0.15, and so on. We find the z-score that corresponds to each of those probabilities. And this is the list of z-scores that we get. Here's our data set. Now what we need to do is we need to arrange our data set from smallest to largest. So the smallest data point is going to get matched up with the smallest z-score of negative 1.645. Then we're going to sketch the scatter plot. Pairing again, smallest data point to smallest z-score. And we get, it's taking a while for it to bring up our picture here. So they said the 52.53. Oops. That's a stray arrow there. That's not supposed to be in there, sorry. So now since the normal probability plot is approximately linear, oops, what happened there? We didn't show our plot. Let me back out of this for a second and see what's going on. There we go. Let's go back here. Okay, so there's the arrows I was needing. This is showing that the 52.53 is the smallest one, and each of them goes in kind like that. Here is our plot. That is approximately linear across there. That's pretty close to a straight line. Again, here's our z-score, negative 1.645, and that value, the smallest value there of 52.5 about, gives us approximately a straight line across our graph. So that's telling us that this is approximately normally distributed. We haven't talked about correlation coefficients yet. This book does it early on. Our course, we put them later on, so we're going to skip over that correlation coefficient. That value being large, close to 1. 1 is a perfect correlation, which means it is perfectly normal. 0.986 is close to 1. Again, we're not going to cover correlation coefficients till later in the course. Transforming data to achieve normality, we can do a z-score as a common transformation, but other things we can do is we can get rid of skewness by using logarithmic transformations. That's beyond the scope of this course, so we're going to stop this recording. We're going to pause right here. We're not going to cover the rest of chapter 7 here. We're going to skip up to chapter 8, dealing with sampling. One last little thing then on our normal distribution, we can use it to approximate the binomial distribution, because the binomial distribution kind of has that bell shape. It's just discrete, so it goes up in steps instead of a smooth curve. And we can use our normal distribution to approximate it by calculating the mean and standard deviation of the binomial distribution. See, that'd be the normal curve going through the binomial distribution. So suppose this bar is centered at 6. It actually goes from 5.5 to 6.5. So to find the probability of being equal to 6, we would find the normal probability of being between 5.5 and 6.5. That would be equivalent to finding the binomial probability of being equal to 6. So let's say we random variables based on n trials, and possibility of success on each trial is p. The mean, of course, is n times p, and the standard deviation is the square root of n times p times 1 minus p. We have to make sure that n times p is greater than 10 and n times 1 minus p is greater than 10. If that's the case, then this curve, this is approximately a normal distribution. So let's say here, premature babies that are born before 37 weeks and those born before 34 weeks are most at risk. A study reported that 2% of births in the United States occur before 34 weeks. Suppose that 1,000 births are randomly selected and that the number of these births that occurred prior to 34 weeks, X, is to be determined. So here N is 1,000 and P is 0.2. Now being premature is not necessarily a successful thing in nature, but we're calling that our success for our calculation purposes here. Can this be normally distributed? Well, 0.02, the 2% of 1,000 is 20. That's big enough. That's bigger than 10. And of course, 1 minus 0.02 is 0.98. That's 980 when you multiply it by 1,000. That is definitely bigger than 10. So we can use a normal approximation here. Calculate the mean and standard deviation. N times P is 20. The square root of N times P times 1 minus P is 4.427. So there's our standard deviation. We want to know what is the probability of the number of premature births will be between 10 and 25. Well, remember we do that continuity correction. That means 10 really goes from 9.5 to 10.5. So we're going from 9.5 here. 25 goes from 24.5 to 25.5. So we're going to 25.5 there. So the probability of that value being between 10 and 10.5 is the normal probability of being between 9.5 and 25.5. So if you're using the table, you find those z-scores, and you look them up, and you subtract the probabilities. Gives us a 0.8836, which is really close to the binomial probability in that case. So the next step, we're moving on to Chapter 8. We're talking about sampling distributions. Now, what we've been talking about so far with our normal probabilities and other probabilities is selecting a single item out of a population. And what is the probability that the value of that single item is going to fall in a certain range? Here, we're talking about taking a sample of a certain size and then looking at the mean of that sample and finding the probability that the mean of that sample is going to fall in a certain range. So suppose we are interested in finding the true mean, mu, fat content of a quarter-pounder hamburger marketed by a national fast food chain. To learn something about mu, we could obtain a sample of 50 hamburgers and determine the fat content of each. Would the sample mean be a good estimate of mu? 50 is kind of a small sample, but we would say it'd be an estimate of that population mean, and we would call that a point estimate. How close is that sample mean to the actual population mean? Well, that's the point of doing these sampling distributions. Chances are it's going to be close, but how close is close? So how do we quantify being close? Well, other samples of n equals 50 have the same sample mean. No, they're all going to be slightly different. There will be variation. The question here is how much will they vary? So to answer these questions is found by examining the sampling distribution. So our statistic here, the number that can be computed from a sampled data. So a statistic, again, is a number that describes a sample. Some statistics we will use will include the mean of the sample, standard deviation of a sample, and sometimes we use the standard deviation of population if we have it. Sample proportion. And the observed value of the statistic depends on the sample we select. So even though we very carefully randomly select that sample, we can get different sample values because each of those samples is going to vary a little bit. So that variability is called sampling variability, and that's part of what we're looking to describe in our sampling distributions. So here we're taking a sample of 20 fish out of a pond, and these are their lengths in inches. Suppose we randomly catch a sample of 3 fish and measure them. So let's say we randomly catch a sample of 3. The lengths are 6.3, 2.2, and 13.3. Now you'll notice we had one value that's pretty small, the 2.2, but another one that's fairly large, the 13.3. And that's the whole point of sampling distributions is when you take it, rather than just selecting one item, which could be small or large, if you select a group, well, chances are that group might have some small values, but there's a good chance there's going to be some large values to average it out closer to the middle. So the sample mean for those 3 in that sample is 7.27 inches. That's a statistic. It describes the sample. Now let's do some more samples. Our second sample has fish of 8.5, 4.6, and 5.6. That gives us a mean of 6.23. That's different from our first mean. Our third sample has a larger mean. We have a sample of 10.3, 8.9, and 13.4. That has a mean of 10.87. So notice all those means are different. There's variability in that sample statistic, but we can predict that variability. So the true mean of this sample was actually 8. So notice those are all fairly close to 8, but they varied a little bit in one direction or another. That is called sampling variability, and that's what we're going to look to quantify here. So we're looking at this fish pond again. There are 1,140 different possible samples of 3 that we could take from this. So what are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 20 fish. There's 1,140 ways to select 3 fish out of 20. Each of them would give us a different mean and a different standard deviation. The means of all of those samples is called the sampling distribution. Now, this is a little misprint here, but that should be a bar over that x. It got slid over to the f, but that's x bar means the sampling distribution of x bar, the sample means. So the sampling distribution of the sample means is considering every possible sample mean of every possible sample of that size from the population. In this case, the sample statistic is the sample mean of x bar. It could be a sample proportion as well. Now let's suppose there's only 5 fish in the pond. Those 5 given below. So we will keep the population size small just to make all the possibilities, less possibilities to analyze. So we find our mean and standard deviation of those fish in the pond. We get a mean of 7.84, standard deviation of 3.262. Let's find all samples of size 2. So out of 5, the number of samples of size 2, there are going to be, you can see here, 10 of them. So our first sample was the 6.6 and the 11.7. That gave us a mean of 9.15. We go through here, we see that we have means ranging from 4.4 up to 10.75. There's variability. And we have those 10 samples. We took all 10 of the possible samples, found the mean of each of them. These numbers right here are the sampling distribution for the samples of size 2. So now let's find the mean of those sample means. If we calculate the mean, we notice it is 7.84. It is exactly the same as the population mean. And that will always be the case. The mean of the sample means, that's the mean of the sample means for size n equals 2 is equal to the population mean. That's always going to be true no matter what the size of the sample is. The standard deviation, however, is going to be smaller. And we'd expect that. If we're taking 2 values, the chances that we get a really small or really large mean are less, because if one of our values is really small, chances are the other one's going to either be large or towards the middle to bring that back in. To get a really small mean, we'd have to have 2 really small values. So that's a smaller chance of getting 2 small values than it is of just getting 1. So that samples, the standard deviation of the sample means is smaller. How much smaller? Well, we're going to compare it to the population standard deviation. We're going to establish a pattern here in a little bit. I'll let you in on a little secret. That pattern is, let's go back here, that this standard deviation of the sample means is equal to the population standard deviation, which is the 3.262, divided by the square root of the sample size. That'd be divided by the square root of 2, would give you that 1.998. So now let's do our sample size of 3 here. Here's all of our samples, and here's the mean for each of them. Oh, that's only 1, 2, 3, 4. There's only 10 of those as well. Oops. We find the means of each of those samples. These values determine the sampling distribution for X bar. Put the bar over the X there. For samples of size n equals 3. What is the mean and standard deviation of these samples? Well, the mean, once again, is the population mean. The standard deviation, since the sample size is larger, the standard deviation should be smaller still. Because if we have 3 items in our sample, the chances of getting 3 that are really small or 3 that are really large is less yet. The chances are some small, some large are going to average out to the middle. Now again, this is equal to our population standard deviation, 3.262, divided by the square root of our sample size. Sample size is 3 now, so it'll be divided by the square root of 3. So what did we notice? 1, the mean always equals the population mean. So the mean of the sampling distribution, or the mean of the sample means, always equals the population mean. The standard deviation of those sample means is always less than the population mean. And as the sample size gets larger, that standard deviation of the sample means gets smaller. So rule 1, the mean of the sample means equals the population mean. Here's rule 2, this is what I was telling you, the standard deviation of those sample means is equal to the population standard deviation divided by the square root of n. Assuming that the sample size is large enough. It usually cannot be more than 10% of the population. Otherwise, we have to do something called a finite population correction. We're not going to get into that at this time. So in this case, the fish pond example, this sample size was more than 10% of the population. So that formula I put up there before, we're just divide by the square root of 2 or the square root of 3, wouldn't quite be accurate because our sample is large compared to the population. So we'd have to use a finite correction factor on that. So let's look at another example here. The mean platelet volume in patients with metabolic syndrome and its relationship to coronary artery disease. So it includes data that is normally distributed with a mean of 8.25 and a standard deviation of 0.75. There's our curve. You can use Minitab to generate random samples from this. We want to get 500 random samples of size n equals 5. So we generate 500 random samples. Actually, we're using samples of n equals 10, n equals 20, n equals 30, and we keep doing that. And what we see here, this is for if n equals 5, we get that distribution of sample means. This is for n equals 10, n equals 20, n equals 30. You can see at n equals 30, it is almost perfectly symmetrical. The larger our sample size is, the more normally distributed that histogram becomes. So, general properties, when the population distribution is normal, the sampling distribution of X bar is also normal for any sample size. If it's not normal, if the population is not normal, the sampling distribution will only be normal if we have a large sample size. So is overtime period in an NHL game long enough? So the data here is in minutes from the start of the game to the first goal scored in 281 regular season games. The density histogram is shown below. So there we go. You can see there's relatively large number of items here in the 0 to 4 range. That means the first goal is scored within the first 4 minutes of the start of the game. Very few games where the first goal is in the 56th minute of the game. It is skewed. It has a mean of 13 and a median of 10. So that tells us it's skewed because the mean is larger than the median. So that's positively skewed. We can generate samples from this data. If n equals 5, we get this kind of weird looking distribution. N equals 10, 20, 30. You can see at n equals 30, that's starting to look like a bell curve again, like a normal distribution. As a general rule, each of these histograms has a center at 13 because that's the population mean. The standard deviation gets smaller, the data gets closer together, the larger the sample gets. And again, the larger the sample gets, the closer we are to a normal distribution. When n is sufficiently large, the sample distribution of x bar will be approximately normal, no matter whether the population is normal or not. Generally, we're looking at a sample size of 30 or more. So what is sufficiently large? Well, like we said, sample size has to be at least 30. So a soft drink bottler claims that an average can contains 12 ounces of soda. Let X denote the actual volume of soda in a randomly selected can. Suppose that X is normally distributed with a mean of a standard deviation of 0.16 ounces. We're assuming the mean is 12 ounces. 16 cans are randomly selected and the soda volume is determined for each one. Let X bar be the resulting sample soda mean. So if the bottler's claim is correct, then the sampling distribution of X is normally distributed. The mean of the sampling distribution should be equal to the population mean of 12. Standard deviation should be the population standard deviation of 0.16 divided by the square root of the sample size. We selected 16 cans, so 0.16 divided by the square root of 16 is 0.04. So that's our sampling distribution. Should have a mean of 12 and a standard deviation of 0.04. So the probability of being between 11.96 and 12.08 is going to be that probability based on a mean of 12 and standard deviation of 0.04. We use that because it is a sample mean, not an individual value. If we were selecting an individual value, the z-score would use the 0.16, which is the population standard deviation. But since it's a mean of a sample of 16, we're using that standard deviation from the sampling distribution. So we calculate those z-scores from -1 to +2, and we find that probability. This is going to be the probability of z being less than +2. This is the probability of z being less than -1. We subtract those to get the probability of being between those values. A hot dog manufacturer asserts that one of its brands of hot dogs has an average fat content of 18 grams per hot dog with a standard deviation of 1 gram. Consumers of this brand would probably not be disturbed if the mean was less than 18, but would be unhappy if it exceeded 18. So an independent test grabs 36 hot dogs and tests the fat content. It results in a mean of 18.4 grams. Does this suggest the manufacturer's claim is incorrect? Well, we assume that the claim of 18 grams is correct. Would getting a sample of 36 with a mean of 18.4 be unusual? And what we're going to do is actually find if the probability that mean is greater than or equal to 18.4. If that is a very, very unlikely, a very small probability, then there's an issue here. Now they took a sample of 36. Sample size is larger than 30, so we don't have to worry about whether the population is normally distributed. So we're going to use that sampling distribution of the sample means of x bar. To find since the population standard deviation was 1, it's 1 divided by the square root of 36, gives us the distribution, or the standard deviation for the distribution of sample means of 0.1667. And of course the mean of the sample means is just the population mean of 18. So let's find the probability of being greater than or equal to 18.4 based on that information. So that's a z-score for 18.4 of 2.4. Probability being greater than that is 0.0082. That's a really small probability. Since that's a small probability, that's very unlikely to happen. So we're saying our assumption must have been wrong. We assumed that 18 grams that the manufacturer claimed was correct. Under that assumption, we got a result that was very unlikely. So we're saying that the manufacturer's claim is probably not correct. Let's explore what happens in distributions of the proportion, p hat. So we're going to do the following experiment. Toss a penny 20 times and record the number of heads. Calculate the proportion of heads in each set of 20. So we make a dot plot of this graph with a sample size of 20. What would happen if the dot plot, if we flip the penny 50 times? Well, just like with the other ones, that plot is going to look, it's going to look like a bell curve, but the larger the sample size is, the narrower that bell curve will be. So our sampling distribution of P, or P hat, P is the population proportion, P hat is the sample proportion. A lot of textbooks just use P to represent both. It's a little sloppy, but that's okay. So the distribution that would be formed by considering the value of a sample statistic for every possible different sample of a given size of the population. Again, so every possible combination of 20 flips of that coin or 50 flips of that coin or whatever. So in this case, P hat is going to be the number of successes, number of heads, divided by the number of flips. Suppose we have a population of 6 students. Alice, Ben, Charles, Denise, Edward, and Frank. We will keep the population small so that we can do all of the possible samples. So here we're interested in a proportion of females. This is called the parameter of interest. So what proportion of those students is female? Well, there's 2 females out of 6 total, so that's 2 out of 6 or 1 out of 3. Let's select samples of 2 from this population and see what we get. So samples of 2 from a population of 6, there's 15 possibilities. So Alice and Ben, well, that's 0.5, half of them are female. Alice and Charles, 0.5. Alice and Denise, it's a 1.0, 100% of them are female. Go down through, we're going to have some that are both boys, so it's a 0 proportion. There's 0 females. If we take the average of all those, the mean of those sample proportions, we're going to get 1/3, which is equal to the population proportion, 1 out of 3. The standard deviation, however, is a little different. We're going to look at how we find that in just a second. So the rule, the mean of the sample proportions will always be equal to the population proportion. The standard deviation of sample proportions is similar to the standard deviation for a binomial distribution, only we're dividing by that square root of n, so it's the square root of p times 1 minus p over n, all in the square root. Again, the sample size has to be less than 10% of the whole population, or we have to deal with that continuity correction factor, the finite population, not continuity correction, sorry, the finite population correction factor. In fall of 2008, there were 18,516 students at California Polytechnic. Of those students, 8,091 were female. We'll use a statistical software package to simulate sampling from the Cal Poly population. So we're going to generate 500 samples, some with size 10, some size 25, 50, and 100, and we're going to then graph those results. So if the sample size is 10, there's our population proportions of females. Some samples as low as 10%, some as high as 90%. But as our sample size gets larger, here at 100, you can see it goes from only 30% to a little over 60%. So the sample gets narrower and it's more bell-shaped. They're centered around the 0.437 because that is the population mean. So the mean of the sampling distribution will be the same as the population mean. Standard deviations, again, it gets narrower as the sample size goes up, and they become more bell-shaped as the sample size goes up. So we're going to develop the development of viral hepatitis after blood transfusion can cause serious complications. So we're looking at a study on that. Reports that hepatitis occurs in 7% of patients who receive blood transfusions during heart surgery. So 7%, let's do a simulation here. We're going to generate 500 samples of each of those sizes again, and then we're going to graph them. So again, notice this is severely skewed. Now the last example, the first one was relatively bell-shaped. That's because the population was normally distributed. Here, the population is not normally distributed. But again, notice as we get a larger sample, it becomes closer to being bell-shaped. So what happens to the shape as the size gets bigger? We get more normally distributed. So again, a large sample, when n is large and p is not close to 0 or 1, the sampling distribution of p hat is going to be approximately normal. If the p, the population proportion, is really small, close to 0, or really large, close to 1, then we have to have a large sample for it to be approximately normal. The farther the value is from 0.5, the larger the sample must be. We have that requirement that n times p has to be bigger than 10. Or n times 1 minus p also has to be bigger than 10. So that helps us adjust if that proportion is close to 0 or close to 1. So suppose a new blood screening procedure is believed to reduce the incident rates of hepatitis. So we're going to take a sample here of 200 blood recipients. Only 6 out of that sample contracted hepatitis. What does this tell us about our 7% screening? Well, assuming the 7% is correct, what's the probability that we get a sample of 6 out of 200? So 6 out of 200 is 0.03. Assuming the 0.07 is correct, we find a standard deviation. First we do the check. Both n times p and n times 1 minus p, both are larger than 10, so we can use the normal approximation here. The mean and standard deviation, well, the mean is going to be 0.7. We're going to assume that that is correct. Standard deviation, 0.7 times 1 minus 0.7 over 200 and square rooted is 0.018. So now we use the 0.3. We find a z-score based off of that mean and standard deviation. 0.3 minus 0.7 divided by that standard deviation gives a negative 2.22. Probability of being less than that is 0.0132. Now that's less than 0.05. That's a pretty small percentage. So we're going to say that that is evidence saying that maybe that does improve on the rate of hepatitis after transfusion. So that is how these sampling distributions apply. I'll post this video, and I'm going to post another one from another class that I think goes through it a little bit slower and a little bit more detailed examples for you. But that is the gist of this week's material. You guys have a great week.